for size equals 2 to n. Okay, so now we're going to consider how to build bigger optimal binary search trees. Now, we're going to, I can do this with Mr. Kligas and Ryan again, maybe. So suppose we're trying to figure out, oh yeah, nn, it's not here. You actually want 1n. This is the answer. This is the answer this time, because 1n is the cost in an optimal binary search tree on keys 1 to n. So we fill in the diagonal and then we work up. Okay, so Ryan, think about it. You say, okay, Mr. Kligas is saying, well, Ryan, what's the cost of an optimal binary search tree on these n keys? And Ryan says, oh, okay, right. Somebody wrote at a distance. Yes. Okay. Thank you. Yes, it was. So Mr. Kligas asks Ryan, what's the cost of an optimal binary search tree on these n keys? And Ryan says, I don't know. And Mr. Kligas says, well, Ryan, let's think. How could the tree look? Well, it could look, the root could be apple. In which case, you have an optimal binary search tree on keys banana through quince. Okay, so this could be 1 and this could be 2 to n. This is an optimal binary search tree of size n minus 1. Okay, or it could be banana, which is key 2, and then so you have over here an optimal binary search tree on key 1, and over here I forget what it was, grape, I missed cherries and dates, and if there's a fruit that starts with E. Okay, so this is 3 to n. This is 1 key, and this is an optimal binary search tree on 1 key. This is an optimal binary search tree on n minus 2 keys. So if we assume that we have all of the costs worked out for all of the trees of size up to n minus 1, then we can find the cost of an optimal binary search tree of size n by going through all of the possibilities for the root and saying, okay, well, what are the two subtrees? We have their cost calculated, and then we work out the cost here is going to be the cost of this, but then this, all of the weights, all of the frequencies in here, all of the keys in here are getting moved down 1. So you're going to have to take all of the weights in here and add them to this cost again. And then you're going to do the same for this, and then you're going to have this one, which is just going to be the frequency times 1 because it's at the root. Okay? So this goes for size for I equals 1 to n minus size plus 1, I think, right? Because if it goes to, if size is 1, which it's not going to be, but okay, if size is 2, you want it to go to n minus 1. Okay, and then you say, for j equals I have to remember how this goes. I plus size I plus size minus 1 plus we don't need a j. We're going to say j equals I plus size minus 1. Okay? Because if I tell you how big the tree is going to be, and I tell you what the first key is, then you know what the last key is. Okay? But then you have to say, okay, for root equals I to j. Okay? So size is going to sort of tell you which diagonal you're on, because as you on this diagonal it's of size 1. On this diagonal it's on size 2. On this diagonal it's on size 3, and so on, until you get up to n by n, in which case it's size n. And then I is going to tell you which row you're in, and j is going to sort of tell you the I is the first key you're considering, j is the last key you're considering, but then you have to consider all of the ways to take the keys you're considering and split them into a left subtree, a root, and a right subtree. Okay? So, this is going to be, I should have said min equals infinity. Min equals, did I restart? Oh, I didn't restart this. Reset. Okay, so now I have like 8 minutes, so I'm going to reset this to 17. Okay. Okay, the code is going to be in the lecture notes, and there'll be the example filled in with the probabilities and everything like that. Are you seeing how this, so what you're going to do is sort of, you're going to have the root, and then you're going to have an optimal binary search tree, which is from I to root minus 1. And then over here, you're going to have root plus 1 to j. This could actually be empty. Remember, when we saw apple, the left subtree was empty, and then there was apple, and then the right subtree had everything. So you know the cost of this, because this has size at most size minus 1. This has size at most size minus 1. And so you can easily compute this. And then you take the minimum over all of the choices of root. Okay? It'll be written up nicely in the lecture notes. So, how long does this take? Well, what's unusual, the two things I wanted you to see in this case are, one, you're not filling it in row major or column major, you're filling it in diagonally. Right? So you don't just say for I equals 1 for j, I equals 1 to n, for j equals blah blah blah. You have to you do this size thing where you decide, and the size is going to be the diagonal. So that, if you haven't seen it before, it's not easy to come up. Well, it's not hard to come up with that, but it's not what we've seen for the past 2 classes. And the other thing is, for each of these cells, you're doing a minimum over over a set of size things, right? Because you can choose each of the keys as root. So even though the matrix takes quadratic space, it has quadratics n by n, you're going to, if you do this naively, you're going to spend cubic time. Now I think on the assignment, it asks you to implement, I think, does it ask you on the assignment to implement this in quadratic time? I asked something like this last year. No, I think last year I asked them to do it so that you could deal with probabilities of failures. So now I think in this case what you have to use is an observation. So there's this fairly simple algorithm here, which is cubic time, and then Knuth made this observation that if you add stuff to so if you have a set of keys, so you have so Knuth's observation is that if the best choice of root for keys I to J is R, then the best choice of root for keys I to J plus 1 is at least R. So if you have a set of keys and you add stuff on the right, the optimal choice of root cannot go left. Okay? So to make this not an impossible, it's not actually, it's not, I can't remember the proof of this offhand. It's not, I mean, you can believe that, right? It sounds plausible. If you add stuff on the right, then you don't somehow move the root left and make the right, the right subtree is getting bigger. Oh, and yeah, and also, this is true, if you add stuff on the left, then the optimal choice of roots cannot move right. And so how Knuth does this, how Knuth uses this to speed things up, is he says, well, okay, if you've already figured out the optimal root for I to J, and now you're trying to do, and you've already figured out the optimal, so if you have the optimal roots for I to J, and I plus 1 optimal root is R, I plus 1 to J plus 1 is R prime, then when you're working out the optimal root for I to J plus 1, it's going to be between R and R prime. It's not going to be between I and J plus 1. So if you work this all out, you get a telescoping series, everything collapses, and you end up not having to do basically O of n work for each of these cells. It collapses and you end up doing constant work per cell over the whole matrix, so you get n squared time. This will be clearer, and it's actually not that, I can't remember if I described how to do this in the scribe notes last year. So I actually wrote the scribe notes for this lecture last year. Okay. So that's very, very quickly optimal binary search trees. Do you see why? Do you see what? If you understand? Do you see what the problem is? You understand the problem? You get sort of either frequencies or probabilities assigned to each key, and you're trying to build the tree, a binary search tree, so that the keys have to be in order in such a way that it minimizes the number of comparisons you're going to do. And then you can do this using dynamic programming and the trick, but I wanted you to see this trick of you don't just do for I equals 1 to n, for j, you don't fill it in row-wise, column-wise, you fill it in by diagonals, because you do this thing on, if you have the size, if you have the optimal solution for smaller trees worked out, then you can get it at the root. You can get it for a larger key by considering all the possibilities for the root. Okay, so now, yeah, that's leaving me like a little 40 minutes for longest increasing subsequence, which is not great, but we're gonna try. Okay, this problem is easy to understand. Longest increasing subsequence. I need a sequence of numbers. Okay, so I promised that the lecture notes would actually be up for today. I have a meeting for like the next 3 hours, but then I'll try to get them written this evening. So, otherwise maybe tomorrow. Okay, so you have a subsequence which is 5, 3, 2, 4, 1, 7, 9. If I had more time, I should have looked this up. 6, 8, 2, 7, 1, 5. Okay. So if I had time, I would actually look up the example we had before of partitioning a subsequence into the minimum number of increasing subsequences. But let's just go with this, okay? Because, okay, we saw greedy, you could partition it into the minimum number, but here we don't care about partitioning it, we just want to take out the largest subsequence, the longest subsequence that is increasing, okay? So, different problem. That was greedy, this is dynamic programming. That confused a lot of people last year or the year before. Okay, 6 minutes. Okay, so the key definition is, well, what's the dimension of our matrix? This time, one of the nice things we'll see in this problem is the matrix is only a line. It's a one-dimensional array. Okay, so you can have one-dimensional dynamic programming. Frequently, this is something people don't think about. It's possible to miss a solution because you're thinking, I'm going to have a matrix. It's going to be 2 dimensions, and you don't think of like, oh, I can have a matrix and it's 1 dimension. So AI is the length of the longest increasing subsequence LIS that ends at, well, let's say that this, what are we going to call this sequence? S. That ends at SI. Okay? Is anybody there? 20 people. I have like a fifth of my class. Okay, good. Okay, so AI is the length of the longest increasing subsequence that ends at SI. So it's easy to work out A1. So A1 equals 1 because you have the sequence 5. Now, for, I don't know if I should have done this as a special case, but in general, how are we going to figure out what AI is, given that we have A1 to AI minus 1? I don't think we even needed this as a special case. How do we figure out AI? So what we're looking for, if we're going to, now thinking back to that lecture where we were partitioning into the minimum number, we have SI, and we can sort of append it to an increasing subsequence if it's larger than the last element in that increasing subsequence. Right? So here we're going to be looking for something. So if we're looking at this one, if we're looking at 1, 2, 3, 4, 5, 6, 7, 8, if we're looking at A8, if we want to compute A8, are we interested in A7? No, because A7 is the length of the longest subsequence that ends at S7. S7 is a 9. We can't append a 6 to a subsequence that ends with a 9, right? The only thing we're interested in, we can't append something that ends with, we can't append a 6 to a 7. We can look here and here and here and here and here. Okay, so in fact, we can take any of the subsequences that end with a number that's less than 6, and of those, we want the one that's that has the longest, that's the final number in the longest subsequence. So we're going to look at A1, A2, A3, A4, A3, A4, A5. We're not going to look at A6, and we're not going to look at A7. So it's going to be AI equals max Sj. Yeah, maybe I shouldn't do this as a subscript. Let's do it like this. I hope people are familiar with this. So it's going to be Aj plus 1 such that for the values Sj, okay, okay, reset, and now this is going to be 25 again.